Jonas Brothers are back together.
Thank God.
Big move. Yeah, it's crazy. Came out with a single.
Okay, we are officially getting started. How is everyone doing today? Good. I'm glad to be back.
Why'd you go to Oakland?
I had a job interview.
Oh.
I have another one today, so that's why I'm like dressed with a tie. I have my jacket in the car.
If you wear your sunglasses in the interview, they won't be able to read your emotions.
Or they'll just say you're hired.
You know, I thought about wearing just like regular glasses in the interview because like studies show like you have a 33% extra chance of getting the job. But like, I'm not used to wearing glasses. Like I never wear glasses, so I don't want to like be thrown off. Like I feel like I'll do worse because I'm not used to it.
What's your interview for?
It's for a full-time position at Saddleback College today.
What was the one in Oakland for?
It was also a full-time position at a college called Los Medanos College. I don't know if any of you have heard of it. It's really far away from here. It's in Pittsburgh, California, not even in Oakland. But Saddleback is really, really close to Chapman. A lot of people that go to Saddleback transfer to Chapman. So we'll see. I'm keeping an open mind. I work for 6 different colleges. So
Right now?
Right now, yeah.
Oh.
So I'm hoping to get like one job where I'm not like running around between all the different colleges.
Where else do you work?
I work for 5 schools in LA, LA Mission, West LA, LA City, LA Valley, and LA Pierce.
Wow, that's impressive.
Oh, thanks. And Chapman. Chapman's the
Chapman's
only.
the best.
Yeah, I mean, like we get really top students.
Of course.
But it's also rewarding to, work with students that, don't always have, a lot of access to things growing up. So it's actually really, really good for me because I'm working with a lot of different students. So it's actually a challenge to work with all the different kinds of students and then kind of adjust to my current classroom. And on top of that, technology has really made a big difference for students because now all of you have grown up with technology and that has changed things a bit. Okay, I'm getting a little distracted, but we are gonna not have a quiz today to make up for some time because I feel like it's important to get through a lot of things. We never quite finished this section 5.1. I just want to briefly talk about the bottom here. Let's start with number 18. I don't know if any of us finished this, but most probability models use a combination of different techniques for probabilities. And the 2 techniques for probabilities that we've used so far, there are 2 of them. I don't know if you remember what they were. What's the first one? What's the first approach to probability? Does anyone remember? Equally likely. Very good. So that's one model. That was the original probability model. Before any of the other probability models came about, that was the one that was first used. So equally likely, that's the first one. And the second one is what? Do you guys remember? Empirical. Now empirical uses data collected from samples to establish probabilities. Today we're going to look at a model like this one below, which uses a combination of both. In this case, we're looking at the number of people that can possibly be in the Uber pool car. Have any of us done an Uber pool where we share it with other people? Ideally, we'd like just one to just be us and not have to deal with other people in your car. but sometimes there can be up to 4 people in the regular Uber pool. I looked at regular Uber pool cars. Could be 4 other people and the driver, which is 5. Most Uber drivers only drive a 5-seater vehicle. So I collected some data and I used both the empirical and equally likely rule to get these probabilities, and then I calculated their mean and standard deviation. So we're actually going to be using a combination of probability and statistics because we have the equally likely model, we have the empirical model. Which one of those models is more close to statistics? Is it the equally likely model or the empirical model? Which is closer to statistics? The empirical. We actually collect data from people. That's really statistics. The empirical model is really statistics. So you have to use both probability and statistics sometimes together to get our mean and standard deviation. So let's see if we can fill in these words with probability or statistics. Each of these words will be probability or statistics. It says fill in the words with either statistics or probability. So there's 3 blanks. Let's go ahead and form groups of 2 and see if we can fill in those blanks. Either probability, each of these words are either probabilities or statistics.
Statistics. Probabilities.
Let's
Statistics. Again, round 2.
Hannah, why don't we have you sit next to Anna? I don't remember who sits there. Oh, you know what? She's here today, right? Yeah, okay, don't. I just realized she's here. Okay. Let's see if we can get the order correct. Before we got these probabilities, we had to use the empirical method along with the equally likely method, and that was statistics. So the first word is statistics. So statistics here was used to produce these probabilities. Here we have the 5 different probabilities. And then what about mean and standard deviation? Are those statistics or probabilities? Mean and standard deviation are statistics. It's okay, we're learning. It's okay if we make a mistake. So here we did a combination of both. Most of the class from here on out is going to be the combination of both probability and statistics like this. So mean and standard deviation are in fact statistics. Now number 20 says, why was probability needed to compute the statistics of the mean and standard deviation? Well, that's because these probabilities are harder to generate without the empirical. We really need to use the empirical method to generate these probabilities. It's really not easy to do that. In fact, it's impossible to do it with the empirical method. Or sorry, with the equally likely method. You need to use the statistics empirical method. You can't do this just with the, you need both. I keep making that mistake. We need both the equally likely model and the empirical model together to get the probabilities and the statistics. We're going to look at some more examples in the next activity. Do you have any questions on any of these problems before we do the next one? Okay, here's section 6.2. This is actually called, number 19 is actually called a binomial model. I'm going to come back to number 20 because I think if we go over this, it'll help with that example. Okay, let's start with number 1. Today we're going to learn about something called the binomial distribution, which is a combination of the empirical and the equally likely model. Let's see if we can fill in the blanks here using the word bank at the top. So groups of 2, let's go ahead and see if we can fill those words in.
We added together to form a binomial. Two.
Got it. Nice. Muy, muy difícil. Oh, that's the hardest. Especially first time taking Spanish.
No, it's.
Yeah.
Okay, so right now we're going to establish the binomial distribution. It turns out you actually don't need the empirical method at all to construct the binomial distribution, but the empirical method, as we shall see, makes it a lot easier. So first we're just going to start by adding equally likely models together. So the first one was added. I really don't like green. I'm changing that. Okay, okay. How about on St. Patty's Day, I'll write everything in green. How does that sound?
St. Patrick's Day, we won't be here. It's a flawed plan.
Okay, so we're adding the models together, and if we're adding them together, that means if we have a random variable where we have number of heads from 1, and we're adding them together, then we're going to be having the number of heads from 2. So the word 2 was the second blank. So in question 2, we're going to look at first the 1 coin flip. In that case, if we have 1 coin flip, either we get a heads or we get a tails. Now if we have 2 coin flips, things change a little bit. We could either get heads heads, we can get heads tails, we can get tails heads, or we can get tails tails. And if we do 3 coin flips, because the binomial model, we can keep adding the equally likely models together. So we could in fact have 3, and then we have this many different combinations. Either we get all 3 heads, 2 heads and a tail, head, tail, head. So let's go ahead and see if we can fill in these. First of all, what's our X here? Number of heads shown from 1 coin flip. Either we get blank heads or blank heads. 0 or 1. Very good. 0 or 1. Very good. So let's see if we can use the equally likely model here to fill it in, and we can work in our groups.
A lot of friends who go to Boulder. Like trips over there for like
I think so let's say flip a coin, like what's the probability of like a number of
No.
heads show from 1 coin?
Okay.
And there's 2 coins.
What are you doing for spring break? Not going back out to St. Louis.
Well, you're talking about the first one would be 60.
I know.
I know. Okay, so they have 0 heads, which is that case, 1 head, which is that case, or 2 heads, which is that case there. So what's the probability of getting 0 heads? So that would just be that 1.
Oh, we got to. We'll just do it for heads.
Yeah. Yeah. And it could, yeah. A 1. Yeah, well, the probability of 0 is just with heads, right?
Yeah.
Oh, really?
So for 0 heads it'd be 0.25.
Yeah, because the one head would be either there's this one or that one. So
Oh, yeah, yeah.
2.
So like, what are the chances of that?
And then there's a chance of.
So it's 1 out of 4, so that's 0.25 or 1 out of 4. And then what's the chances if one fails? So how many of these games does one? And then how many chances
Yeah,
are
because she
there?
was usually on top of it. She's always here.
0.25.
Yeah, she's really sick.
What do you guys need to know?
Okay, let's start with the first one. If we flip the coin once, either we get 0 heads, which is if we get a tail, or we get 1 head. So this is going to be 0 or 1. And the probability of getting 0 heads is getting the tails, which is 1 out of 1, 2. So it's 1 out of 2. Likewise, if we get 1 head, again, that's 1 out of 2. I'm just going to use fractions here. I mean, you could have done it like this. That's fine. Okay, next, if we do the coin twice, either we get 0 heads, which is if we do 2 tails, or we get 1 head, or we get 2 heads. So it's 0, 1, or 2. And the probability of getting 0 heads, well, that's the tails case, the double tails case, so that's 1 out of 1, 2, 3, 4. So it's 1 out of 4. And then the probability of getting 1 head, well, there's how many options of getting 1 head? This option is the first option 1, and this is the second option, so there's 2 options of getting 1 head out of 1, 2, 3, 4 total. So this is going to be 2 out of 4. And then likewise getting 2 heads is this case over here, which again is 1 out of 4. So we get 0.25, 0.5, and 0.25. Okay, last one. We have 0, 1, 2, 3 for seeing the pattern. The most we can get is 3 heads, the least we can get is 0 heads. Probability of getting 0 heads is, how many of these have 0 heads? 1 out of 1, 2, 3, 4, 5, 6, 7, 8. So it's 1 out of 8. Why is it not writing? It's being weird. Sometimes it does this. There we go. 1 out of 8. Okay, and that is, I didn't round it, so I got 0.125. You're probably going to notice a pattern. Getting 3 heads is also 1 out of 8, which is also 0.125, because that's the triple heads case, the one that's the HHH. And the probability of getting 1 head would be this one or this one. So that's 2 out of 8. Sorry, there's 3 out of 8, because we see that. It's this one, or this one. So there's 3 out of 8. And this one here is also 3 out of 8. And so that is 0.375. Okay, so this is called a binomial distribution. Now we need to label the terminology used in a binomial distribution. So in question 2, what was the probability of obtaining a heads? Go ahead and write that down. That's called the probability of blank. And the probability of blank is denoted P, and the number of trials is denoted as blank. So let's see if we can fill this in. Note that I just want to point out real quickly, before we fill these blanks in, notice here that I said create a probability distribution. for when n equals, this is a mistake. This should have been from when n equals 1, 2, and 3. Because we show it for the 1, for the 2, and for the 3. Okay, so let's go ahead and fill these blanks in, groups of 2.
The number of trials.
Okay.
Yeah. Oh, I figured 40 minutes.
What was the probability of original?
Yeah, and then this would be Q, I guess. Oh, no, you use that word.
Okay, one of them doesn't use the word bank. Only one of the blanks doesn't use the word bank.
I think it's the Q.
N is the 1, 2, and the 3.
Is there a probability of obtaining
Probability of being heads can't be n because n is going to be a whole number like 1, 2, and 3, and probabilities have to be between 0 and 1. The first. What's the probability? Yes. Yeah.
Is it pre-read or something?
I'm going to go ahead and just go across because I did a lot of questions. Okay. Before we did the 1 coin flip, 2 coin flips, 3 coin flips, what is the probability of obtaining a heads? 0.5. So that's what this one was asking for. This one's just 0.5. That's called the probability of, what did we want in this example? Did we want heads or tails? So what was the success? Getting a heads or tails? Heads. Very good. So the probability of getting a heads is called the probability of success. So that's a success. We consider it a success. We don't want to get a 0. We want to get a 1. That means we're successful, at least in this first one. The probability of success, we denote that as P. And the number of trials, in this case, we just flipped the coin once, so the number of trials was 1. In this case, we flipped the coin twice, the number of trials was 2, and in this one, we flipped it 3 times, so the number of trials was 3. That is the symbol N. If we're wondering about the other symbols, Q is the probability of failure. We didn't use, you don't really need that, but I'm going to point it out that Q is the probability of failure, if you're interested in that additional information. Now we can actually do this in Excel with the binomial dist function, where you put your x value first, and you put your NP, and then you put the word false. We're going to talk more about why we use the word false there in a second. So let's see if we can rewrite all of the probabilities that we just obtained using the Excel notation. So groups of 2. So what was P, and the whole thing is going to be, we already defined what P was. Probability of success, and we defined it as 0.5. And then N depends on the number of trials.
So it'd be like, okay.
Yeah, I'm going to do the first one for us because I think we need a little bit of a jump start. So it's going to be equals binom.dist. The x value, what's my x value in the first row? 0. Good. N is number of trials. This is which number of trials case? Good. It was the first one, the 1 coin flip. The number of trials was 1. Good. And P is the probability of success. Our probability of success, if we look at our problem here, probability of success is 0.5. So I'm going to put a 0.5 here. and then false. Okay, so see if we can fill the rest of them in. Yes, because we're looking at the same situation, which is getting the same software. Exactly.
The number of flips. So what? Right. It's the number of flips.
Okay, the second column gets a little trickier. I'm just going to put equals b dot d to save room. Again, our x value here is 0, but what's our n for the 2 coin flips? 2, good. Probability of success. Is the probability of obtaining a heads for 1 coin flip still 0.5? Yes, so we're still going to use that same probability of success being 0.5. So we're going to keep it the same the whole time. So again, we're just going to put 0.5 and then again false. Yes.
Other than coin flips, where could we use probability distribution?
Binomial distribution?
Yeah.
It is used a lot of places. Anytime you're repeating something. So in this case, we're repeating the coin flip, but maybe we're picking somebody with blue eyes, for example, from the population. So we're going to keep picking that same person with blue eyes. Probability is still going to be the same. If we take every single person in the universe, it's still going to be the same probability every time we choose that person with blue eyes. Same thing with maybe, actually a good example is when we go to work, we either have a red light or a blue light. So probability, okay, it does kind of change a little bit. So it wouldn't be as good to use that one. But if the probability of getting a red light was the same every time, again, you could look at the number of red lights out of the total, which again would be 0, 1. Like if you had 3 lights that you went to work, you would now look at the probability of getting 1 out of the 3 versus 2 out of the 3 versus 3 out of the 3 red lights. Does that answer the question?
Yes.
We're going to do more examples. Okay, I'm not going to fill any of the other ones in. I'll fill in one more. I'll fill in this one over here. So this one's going to be equals binom.dist, x value, 3, number of trials, 3, probability of getting a heads is still 0.5, and then false. I'll do this one too, binom.dist. This time our x value is 2, still 3 trials, 0.5, probability of getting a heads, and then false. Okay, this is the criteria for the binomial distribution. The probability of success in each trial. Oh gosh, I must have gone hiking. I had the word trail there. Anyway, go ahead and A or B. This is a poll everywhere question. A or B, one of them means changing, the other one means stays the same. 50-50. We have 13 people in the room. Okay, I'm going to go ahead and show our results. A was the correct answer. The probability of the heads had to have been the same every time. What's the probability of getting a heads? 0.5. It never changed. As long as it stays the same and it doesn't change, you can have a binomial distribution. Okay, so we're gonna now classify, this is actually gonna help answer Anderson's question a little bit more, because we're gonna look at we're gonna look at 4 examples and we're gonna try to decide, is this a binomial distribution or not? If it isn't a binomial distribution, you need to decide what was violated. Was it because the probabilities were changing per trial? Or maybe there wasn't a probability of success at all, which would make it impossible to do a binomial distribution. If it is a binomial distribution, you need to identify the probability of success and the number of trials. So again, for each of these examples, if it is binomial distribution, you need to identify the number of trials, probability of success. And if it's not a binomial distribution, you have to decide what was violated, the first or the second group. Okay, groups of 2.
Yes or no?
It's basically what there was in
We can't use a binomial. So probability of, there's more probability of success. Yeah. Like if you look at the individual probabilities of the numbers, and then use that to find the probability. Some numbers, no, can't use
the other brown people.
because the Q probability of success or has to do with success.
I got it.
You get where like their chances go up because like that percent of sex is taken out. So that's why he is yes. All the brown people. Yes. You spoilers and shit. We're doing your spoilers. Okay.
This one, alright. This one's fine, alright. Yeah.
Oh, okay.
Wait.
It's
Okay.
kind of close.
I don't know. Oh.
Oh, really? Could be just.
What kind of spelling? I guess it's what
Yeah, this one.
Some of them it was.
I mean, but what's that? And like the dog, and then like the maybe. I guess it's fine.
So we know B
Is that
definitely.
Yes, I'm offended, and I gave them my cards.
They should already have your name on file.
Right?
So just look it up.
They should remind you of the link. Yeah, they can look at your card.
Okay, if we were to do number A, you're gonna be rolling the die how many times? 3, but is there a probability of a success every time you roll the die? No, because there's a probability of getting a 1, there's a probability of getting a 2, there's a probability of getting a 3, but it's not success or failure. There's 6 different options as opposed to just success or failure, which is how many options, success or failure? 2. Where do you think the word binomial comes from? It comes from the word 2. So number 1 is there's no probability of success. So the answer was no. No prob of success. Okay, second one. Is the second one going to be binomial? Again, we're rolling the die 3 times and we're looking at the number of 1s. Is there a probability of success this time? Yes. What's considered a success? Getting a 1. And what's the probability of getting a 1? 1 out of 6, so you need to write this down. So this one's yes. So our probability of success is 1 out of 6, which is, I'm not going to write that as a decimal. Forget it. And number of trials, n equals 3, because we rolled the die 3 times. Did everyone finish C or D, or do we want to just a minute to finish those up? Okay, I'll do them on the board. Okay. Number of people selected without replacement from 17 people. Is there a probability of success in this case? Well, kind of.
Well, how do you know what number?
So this is now where we're going to need to use the empirical probabilities to figure out what the probability of getting the person with blue or brown eyes is. So we're going to need to use empirical probabilities to figure out what the probability of selecting somebody with brown eyes is. How about let's use the class brown eye probability. What was the class brown eye probability again? Let's, does anyone have their notes from that day? The probability of brown eyes, we did that on the 5.1 activity, which was Introduction to Probability. Does anyone have that activity? Remember what the probability of getting brown eyes was?
Oh yeah, I was like doing something. It was I scratched it.
There we go, okay. It was 6 out of 17. Okay, you could say that this was the probability of success, but what's the problem? You're choosing them without replacement, so let's say you choose somebody with brown eyes. Is this probability going to change?
Yes.
Yes, because let's say you choose a brown eyes person, brown eyes. Now your probability of brown eyes is good, 5 over 16. So, because this is going to go down. You selected one person, so now there's only 5 brown eyes people left. And again, you selected one from the 17, so it went down to 5 out of 16. So why is this not a binomial? What rule was violated?
It's not like equal every time.
Good. Which one is that? Is that there's no probability of success or probabilities change for trial? Probabilities change for trial. Exactly. Without replacement, your probabilities are gonna change per trial. Because when you select the person, you don't put them back. So you throw off the probabilities. Okay, what about D? This time we're replacing the person every time we select them. So what's D? Yes or no? Yes. Our probability of success is the probability of getting somebody with brown eyes. And what was our empirical probability of getting somebody with brown eyes? 6 out of 17. So the probability of success is 6 out of 17, and n equals, how many times are you going to select somebody? What? If we're 17. Oh, actually, you're right. I didn't really specify.
You chose like 3 people for an experiment out of 17, and you get 3.
Yeah, you know, you could have, let's just say you're selecting 17 people to make it easy. Technically, you could select as many as you want. So we're replacing them this time. So we're going back into the population and we're going to take somebody again. So then it's going to be 1 out of, no, it's going to be 6 out of 17 each time we select somebody, and then we put them back. Select another one, it's going to be 6 out of 17, put them back. Again, select another person, 6 out of 17 for a total of 17 times. That was a good question. Any other questions on that one? Do we have any questions on the binomial probability? Now's a good chance to kind of check in if we're kind of stuck on something. Okay, now we're going to look at an example. Oh, I changed this problem actually. I changed it to loses 10% of the packages to make it easier. Okay, so now we have a 10%. The express house delivery uses 10% of the packages. Identify N and P, and then is the P an equally likely or empirical probability explain? You snuck back in here. Or have you been in here like for a long time?
I've been here for a while now.
Oh, okay.
I was right in the bathroom.
I didn't even see you come in. Okay, so what would probability of success?
That's what I got.
So let's consider losing the package of successes. What we are talking about is always going to be the success. So whatever is stated in the problem is going to be success, even if it's negative. Like losing a package is bad. But because we stated in the problem that way, that's going to be our probability of success.
10% of 10.
Which would be 10%, which is 0.
Oh.
Good. It's 0.1.
This one?
Success is always what's stated in the problem, not whether it's good or bad. Losing the package is bad, but the problem is success. I think that's what was stated. The 10% of the packages must have come from some sort of data. Exactly. What did you say?
You said equally likely.
The 10%? Where do you think they got that 10% though?
From the data.
So when you use the data, is that equally likely or empirical?
Empirical.
Empirical.
All right.
Okay, identify P and N. P is the probability of success, which is what's stated in the problem. Success is going to be losing a package. What's the probability of losing a package? 0.1. Good, 0.1. So the first one is 0.1. And then how many times are we mailing a package out? 10. So we're going to be repeating this procedure. It's like 10 coin flips, essentially. We're repeating the package thing 10 times. So N is going to be 10. And is the P equally likely or an empirical probability? If it was equally likely, then it would be like, you'd be equally likely whether we lose the package or we don't lose the package. But we're saying that only 10% of the packages get lost. So that's not an equally likely probability. That's coming from data analysis. The package people, they took every single package and they looked at the number that were lost to get the 10%. So that's an empirical probability. Please write down why you believe it to be an empirical probability. Okay, something that's going to help us also besides the probability distribution is the cumulative distribution. Do we remember cumulative distributions? What does it mean when you have the cumulative distribution of 1? You did what with the previous probabilities? You added them together. So this cumulative of 1 is the 1 and the 0 added together. So let's see if we can fill in these missing pieces of the chart using cumulative distributions.
Wait, give me again. What's speed?
So the cumulative distribution of 1 means to add the probability of getting a 1 to all the previous probabilities. In this case, we just had the probability of getting 0. So we added the probability of 1 and 0 together to get this one.
Okay.
We're going to have to use like some sort of subtraction scheme. Once this gets to 1, that means anything else that you add here, this has to stay at 1. The cumulative probability
So this and this is that. And then this one would be. Yeah.
That means that that means there's a 100% chance that is 5 or less packages equal that.
So this minus that is that.
Okay, let's start with this one here. So we have 0.349 plus blank is equal to 0.736. So basically we just take 0.736 and we subtract 0.349 to get 0.387. Any questions on how I got that first? Okay, now to get the cumulative distribution of 2, that means we have to add the 2 with the 1 and the 0. So the cumulative distribution needs to take the 2 probability and then add all the previous probabilities. We're adding the 2, the 0, and the 1 together. So if we do that, we get 0.349 plus 0.387 plus 0.194, and we end up with 0.93. Another thing you could have done is you could have taken the 0.736 and had what? The 0.194. We could have added the 0.194 to the, so another thing we could have done is we could have added this 0.194 to the 0.736 and got 0.93. Okay, next, we want to take this and we want to get this missing one here. Okay, there's a couple of things we can do. We can take the 0.987 and we can subtract the 0.349 and we can subtract the 0.387, or we can subtract the 0.194. What's an easier way to do this? Yes. Good, you could just subtract the 0.93 from the 0.987. So that's what I'm gonna do. I'm just gonna do 0.987 and I'm gonna subtract 0.93 and I get 0.057. And lastly, I'm going to add the 0.011 on to the 0.987. And I'm going to get 0.998. And then I'm going to do 1 minus 0.998 to get 0.002 here. Okay, any questions so far? Does anyone want me to redo any of these ones? Okay, now we hit 1. Once we hit 1, can the cumulative distribution ever be more than 1? No, that means there's a 100% chance that you lose 5 or less packages. That means you can't lose 6, 7, 8, 9, or 10 packages. The rest have to be zeros. So these are all going to be zeros. And these are all going to be 1s. Yeah. Then once we're ready to go on to number 10, use 2 different methods to find the probability that more than 1 package is lost.
So we just subtract. 1 minus. So we look at that piece, because that'd be well over that. It's like pretty much like
More than 1
this is the probability that 0 to 4. So if we just like more than 1, then 0 to 5, 1, 2 to 5, so it's this. Yeah, so the other would be adding this one, which would give us the same thing.
You want to add the 2, 3, 4, 5, 1?
Yeah, that's 2 through 5 for sure.
Oh, the other way would be to do
Or
1
2 through
minus
5.
0.
So
Sorry, 1 minus 0.736. That's what it is. What do you do 1 minus 0.736?
Why don't you do,
So the C is the 1 or 0. The P is just the 1.
oh,
You want to use the C column to do them. You had it right.
yeah, I have more.
Okay, so let's go ahead and do this. What does it mean more than 1? Does more than 1 mean 1? No, it's P of 2 plus P of 3 plus dot dot dot. If you add the 0.194 plus 0.057 plus 0.11 plus 0.002, you end up with the value 0.264. But there's a much easier way to do this. You know that the 2 or more is hold on. You know that the 1 or less, this is what we know. We know 1 or less is this one here, 0.736. That means 1 or less package. Exactly. 1 minus 0.736 would be the other method. So doing 1 minus the probability, or sorry, the C of 1, which is 1 minus 0.736, also gives you 0.264. Okay, questions on number 10. Okay, next we want the probability that 2 to 4 packages are lost. Also, see if you can fill in number 12 first. I think number 12 is probably easier to do than number 13. There. Or what would be right here, number 12?
Not sure.
So this one should do the probability of more than one package we did in 1 month is the probability.
Yeah.
1 or less packages. Good. Got it. Are you gonna work on this?
Yeah.
No difference between this and relative frequency.
No, probability. Just say here. Okay, number 11, first method. Use two different methods between 2 and 4. So between 2 and 4, that's this here. So what do I want to do with these 3 probabilities? I said 2 to 4. So what do I want to do with these 3 probabilities? Add them together. So 2 to 4 means to add the 3 probabilities together. P of 2 plus P of 3 plus P of 4. And when we do that, we get 0.194 plus 0.057 plus 0.011. And when we do that, .262, but there's a different way we can do this. We know that this probability, the 0.998, is the 4 added all the way to the, how do we get to 0.998? We're adding the 4 to the 3 to the 2 to the 1 to the 0. So if we want just the 4 to 2, what can we do with the 0.998? Well, if we subtract it from 1, we're going to get 0.002, which is this stuff. But we want these 3 values added together. So we're going to have to subtract something.
Subtract 0.998 from 0.736.
Good. If you take the 0.736 away from the 0.998, you'll get the value. So it's the 0.998 minus the 0.736. And again, that gives you 0.262. Okay, let me explain this one more time. This 0.998 is all of these added together, and the 0.736 is these two added together. So we take this, which is these two, away from this, which is these three, we're left with the 3 in the middle. So we're doing C of, it was C of 4 minus C of 1. And that gave us the 0.998 minus the 0.736. Any questions on how I got that again? Okay. Lastly, if you want the probability that x is more than a, what did we do? We did 1 minus the probability that x is less than or equal to a. And the probability that x is between a and b, we took C, we were looking between 4 and 2. So this was a probability between 2 and 4. We took the b probability, which is C of 4, which is the probability x is less than or equal to b, and then we subtracted the probability of the a probability. But the a probability is that a, the thing is, here we took 1 away. We didn't take 2 away, we took 1 away. So what symbol can I put here? Is it less than or equal to a? Well, C of 1 is a less than, has a less than built into it. So this is going to be a less than symbol. But if we're just good with the C being 1 less, notice how the C is just 1 less than the value here. So we have between 2 and 4. The first one was 4, but the second one was 1 less than 2, which is 4. We did C of the second value minus C of the 1 less than the first value, which is 2. Okay, for the remainder of class, I want us to just get the activity started, which is basically doing it on the computer. By the way, this last one here should be true. If you want cumulative probabilities, you need to write true, not false. Let's see if we can get the last page of the activity here started. So what I really want us to do is to do 2 probability charts, one with the regular probabilities and then one with the cumulative probabilities. So let me quickly kind of get us started. And it doesn't matter which version of Excel we use. If you'd rather just use your laptop, that's fine. So you're going to want to make a chart. In this problem, 10% of all luxury cars are black. If 20 cars are randomly selected, that means we're going to have an X column going from 0 all the way to 25. And then we're going to put our P of X column here, and we're going to put our C of X column here. So to do the P of X column, it's going to be binom.dist. We want to put our X value in first, which is 0. So click on the 0. And the number of trials, what was our number of trials if we're selecting 25 black cars? If we're selecting 25 cars, how many times are we selecting a car? Our number of trials is going to be 25, which is the number of cars we're selected. And then we want to put the probability. What's the probability of selecting a black car? Good, 0.1. And then I want to put false to indicate I don't want cumulative probabilities for the first one. Okay, second one here. equals binom.dist. What number again is my x number? It's going to be the 0. Number of trials is 25. Probability of success 0.1, and cumulative this time, if we want the C of x column, the cumulative is going to be true. Okay, instead of doing it individually for each of these, drag it down by going to the right-hand corner and then going down like this. Same thing if this one, go to the right-hand corner and drag it all the way down. Okay, I'm going to come around to help. See if you can get some of the first few questions done.
When I put 0.
Yes.
Sorry.
Number of trials. We're selecting 25 columns.
Oh wait, it's supposed to be 0.
There's probability of success, which is good. And for the P of x column, it's going to be false, and for the C of x column, it's going to be true.
So I'm the P of x.
Yes.
So do I do just
So
do I just
FALSE, you have to put, I think, the whole.
And then there's the enter.
Yes.
I do that.
You didn't enter the probability of success.
oh, do we make it true or
I'll
false?
drag it down?
For which one?
For the P of x, yeah.
False.
Okay, so you click on that one there, and you go to the bottom. There we go. Do you want to go all the way to 25?
You did it.
So he'll let you do it, but you'll have to type it, and you'll have to type the 9.
Oh, and to like select A2, which was just a 0. And then. And then you put the number of trials, which is 25, and then you do 0.1, which is the probability. And then for P of x it's false, and C of x is true.
The first column is the 0,
These fives.
unfortunately, you have to type in 0, not 5. So you have to type that.
Yeah, exactly 4.
Okay, once you have your chart, start answering the questions.
When I did this one, it came out this.
Yeah, you know what, you're right. And I'll do a Twitter and then.
Instead of 0, you have to.
It's just the 4 value. Because I wrote exactly.
I'm opposed.
At least 5.
Okay, it says 0.
That's when you add up all the 5. Oh, okay.
So 0.
So you have to click on the 0.
Oh.
How do I do this?
Then are we
Oh,
trying?
no.
Same thing, but then you type in true instead of false.
Are we sending those to you?
I'm gonna just take pictures of whatever you have written on the
Can I
desk.
still click the 0?
Yes, you still click the 0.
Excuse me.
You can either do the sum and then highlight the you have to highlight the The other way to do that would be to do the 1 minus
I just did it like
Oh, 0.1.
Wait, just like.
Oh, or just like all of them? Oh.
Oh, I have a question. First of all, is this the first stuff in the class? We only.
I haven't finished
So
this.
let's just as long as you have
Oh, okay.
I mean, the
Is
rest
this?
of these are the same boxes.
Okay, but for this, so it's like these five larger blocks, so I just equal five blocks and 2 more zeros.
Yeah, at least, at least 5 would be add your 5, 6, 7, 8, 9, 10, 11, 12.
Oh, okay. So then, at most, 6, that's when you do 6, 5, 4, 3, 2. So at most.
At most.
Okay, okay, thank you.
Or you could do it the other way.
Okay, so I do equal 1 minus. I do the C that's 5. Okay.
So when it says exactly 4 larger blocks, it's exactly.
Exactly, that's the exact.
And then when it says the first one, sorry, so like 5. And you just have like.
Exactly, or you could do 1 minus 0.902. So the two options are either to add the 5. So either to add the 5, the 6, the 7, all of these together, or the 1 minus the 0.902.
Okay.
I think it's my next line. I see where you want to start it at the first one.
Okay, then you'll be fine for the homework.
Alright.
Can we check mine?
Just go ahead and go.
Thank you.
What's the shortcut one? It's like, wait.
Okay, so the shortcut formulas are for the mean and standard deviation. What I'm gonna do is I'm gonna add, it's super easy. The formulas are like, you literally just plug values into the formulas. So I'll just upload a video that explains how to do that.
Am I good?
If you feel comfortable about the homework, then you can go. I'm just gonna just check to see how many you did today. Exactly 4 would be this. 0, 1.
Oh, yeah. we really just laughed.
So for this one, like how much is that?
So we can evaluate that.
Oh, wait. Got it.
So it says at least 5 black probability. So what I do, I did like the sum, just add up. I go over here and at least 5, so I just drag right here. Add those, yeah, because the probability only is like, this is the probability of 5 are black, 6 are black, 7 are black, and saying at least 5, yeah, so 5 or more, so then that's, so it's at most 6, so, yeah, it would be 6, and, or,
I'm really bad
yeah,
about my
6.
Get like a math.
Yeah, I just want to make sure that you guys got it started. The homework is going to be just like this, and then the other option.
Oh, yeah. I'm like, I got it.
This one's the same age.
Oh, they didn't give us an action.
Yeah, no, I just think it.
I'm
David, you're-
scared. I want to go with the tables I have.
Thank you.
Sorry, fine, but I'm saying.
Are you guys able to get it started?
Is this right?
Yeah, that's correct. So it would just be answering like those kind of questions. Do you think you guys could do the homework on that? Okay. And then the mean and standard deviation, you use the shortcut formula. So I'm gonna put a video that just gives you the formula, and then all you do is plug the values into the formula and you get the answer.